Tonight, we're going to talk about what lies beneath the storms of Jupiter. For 4 centuries, that world has hung in our telescopes like a lantern at the edge of the familiar solar system, banded in cream and rust and ochre, spinning so fast that its equator bulges outward like a marble squeezed gently between 2 fingers. We have watched it longer than we have watched almost anything else in the sky. Galileo turned his crude glass toward it in the winter of 1610 and saw 4 tiny stars trailing behind it. And within weeks he understood that they were not stars at all, but moons, worlds circling a world, the first proof that not everything in the heavens revolved around us. Since that night, generation after generation has returned to Jupiter, sketching its face, timing the drift of its cloud bands, measuring the slow rotation of that great ruddy eye that seems to stare back at anyone patient enough to look. And yet, for all those centuries of watching, we understood almost nothing of what we were seeing. We assumed the storms were a kind of weather, and weather implied a surface beneath. Something solid, something the storms rested upon, something that might one day be mapped and named the way we mapped, and named the continents of our own world. We imagined Jupiter as a giant Earth wrapped in an unusually thick and turbulent atmosphere. We were wrong, and the wrongness was not a small thing. It was the kind of error that changes what a planet means. What would we find if we could peel back those coloured bands and descend into the dark? What is Jupiter made of all the way down? Is there a down at all, in any sense we would recognise? And if the storms we have watched for 400 years are not resting on a surface, what are they? What holds them in place? What feeds them? What lies beneath? By the end of tonight, you are going to understand exactly what a spacecraft named Juno has discovered hiding beneath those endless storms, why the answers it found were stranger and more beautiful than anyone expected, and why the world we thought we knew has turned out to be something far more alien and far more wonderful than the giant marble we imagined. Before we begin, if you love exploring the deep mysteries of our solar system as much as we do, take a moment to like the video or subscribe. It is a small thing, but it helps this channel reach more curious minds drifting through the night. Now let us begin. The story of Juno begins, as so many stories of discovery do, with a question that nagged at the people who ask questions for a living. By the early years of this century, we had visited Jupiter many times. Pioneer 10 swept past in 1973, the first human-made object to cross the asteroid belt and survive, returning grainy images of a world that looked almost like a watercolour painting left out in the rain. Pioneer 11 followed a year later, swinging around the planet and using its gravity to fling itself onward towards Saturn. Then came the Voyagers, twin spacecraft launched in the late summer of 1977, each carrying a golden record etched with the sounds of Earth, each destined to fly past Jupiter and reveal its moons and its storms in detail we had never imagined. Voyager 1 arrived in March of 1979 and Voyager 2 4 months later, and between them they transformed Jupiter from a smudge in a telescope into a place, a world with volcanoes erupting on one moon and a cracked ice shell on another, a world where the Great Red Spot turned out to be a storm large enough to swallow the Earth twice over, a world ringed by faint threads of dust we had never suspected. And then, in 1995, a spacecraft named Galileo arrived not just to fly past but to stay. It dropped a probe into the Jovian atmosphere, a small capsule that plunged through the cloud tops and sent back data for nearly an hour before the heat and pressure crushed it into silence. For 8 years, Galileo orbited Jupiter, studying its moons, mapping its magnetic field, watching the slow churn of its atmosphere. It told us more about that world than all previous missions combined, but there was something Galileo could not do. Its orbit was designed to study the moons, and so it swung wide of the planet itself, never dipping close enough to peer beneath the clouds in the way scientists had begun to realize they needed. The instruments of the 1990s could see the surface of the storms, could measure the temperature and composition of the upper atmosphere, could trace the magnetic field from a respectful distance. But Jupiter kept its secrets locked beneath that painted skin. What lay below the clouds? How deep did the storms go? Was there a core at the centre, a dense ball of rock and metal like the one at the heart of Earth? And if so, what was it made of? And how did it form? And what could it tell us about the birth of the solar system itself? These were not idle questions. Jupiter is not just the largest planet in our solar system. It is the oldest, or very nearly so. It formed first, before the Earth, before Mars, before any of the rocky worlds we call home. It gathered itself out of the disk of gas and dust that surrounded the young sun, pulling in hydrogen and helium by the ton, growing so massive so quickly that its gravity shaped everything that came after. The position of the asteroid belt, the size of Mars, perhaps even the delivery of water to a young and barren Earth, all of these may have been determined by Jupiter's early growth and its long gravitational reach. To understand how the solar system came to be, you must understand how Jupiter came to be. And to understand how Jupiter came to be, you must understand what it is made of all the way down. The question was deceptively simple. Does Jupiter have a core? And if so, is that core a dense ball of heavy elements, a seed around which the rest of the planet accreted, or is it something else, diffuse, diluted, smeared outward into the surrounding layers? The answer would tell us how giant planets form, whether they begin as rocky seeds that gather gas or as collapsing clouds of gas that swallow rock. It would tell us whether Jupiter's birth was gentle or violent, whether it assembled itself slowly over millions of years or came together in a cataclysm. But to find that answer, a spacecraft would have to do something no spacecraft had ever done: fly close enough to Jupiter to map the tiny variations in its gravitational pull, variations that would reveal the distribution of mass hidden beneath the storms. And so Juno was born, a mission designed not to look at Jupiter, but to look through it. The spacecraft that would become Juno took more than a decade to design and build. It was not a large machine as interplanetary probes go, about the size of a basketball court when its solar panels were fully extended, but only a few meters across at its core. It was built around a spinning hexagonal body, a design chosen because spinning spacecraft are stable and simple, requiring less fuel to maintain their orientation than spacecraft that must constantly adjust themselves. And because Jupiter lies so far from the Sun, farther than any solar-powered spacecraft had ever ventured, Juno's 3 great solar panels had to be enormous, each nearly 9 meters long, covered in thousands of photovoltaic cells designed to harvest every stray photon of sunlight that reached that distant world. The instruments it carried were not designed to take pretty pictures, though it would take those too. They were designed to measure things that could not be seen. A microwave radiometer would peer through the clouds and measure the temperature and composition of the atmosphere at depths no camera could reach. A pair of magnetometers would map the planet's magnetic field in 3 dimensions, tracing the invisible rivers of charged particles that flowed around and through the Jovian system. A gravity science instrument would track the spacecraft's motion with exquisite precision, measuring how Jupiter's uneven mass tugged Juno this way and that, revealing the hidden structure of the planet's interior. And a suite of other sensors would study the auroras at the poles, the charged particles trapped in the magnetic field, the faint radio emissions that crackled from the planet's depths. Juno launched on a clear August morning in 2011, rising from Cape Canaveral on an Atlas V rocket, climbing through the Florida sky and out of the atmosphere and into the long silence of interplanetary space. But it did not fly directly to Jupiter. The rocket that carried it was not powerful enough for that. Instead, Juno looped outward into the solar system, swinging past the asteroid belt and then falling back toward the Sun, using the gravity of Earth itself to fling it onward. In October of 2013, it swept past our own world, gathering speed, stealing a tiny fraction of Earth's orbital momentum, and finally had enough velocity to reach Jupiter without any more help. The journey took nearly 5 years. 5 years of drifting through the dark, of engineers on Earth checking and rechecking the systems, of waiting and planning and hoping. And then, on the 4th of July in 2016, Juno arrived. The final approach was a thing of terrifying precision. To enter orbit around Jupiter, Juno had to fire its main engine for 35 minutes, slowing itself just enough to be captured by the planet's gravity. If the burn failed, or fell short, or came too late, the spacecraft would sail past and be lost forever. But the engine fired exactly as planned, and Juno slipped into a long looping orbit that would carry it closer to Jupiter than any spacecraft had ever been, skimming just a few thousand kilometers above the cloud tops before swinging back out to a safer distance. That orbit was no accident. It was designed with great care to accomplish something no previous mission had attempted. Every 53 days, Juno would dive in close, racing over the planet's poles at tremendous speed, gathering data during a few frantic hours before climbing back out into the relative safety of deep space. Those polar passes were essential. Jupiter's equator is wrapped in lethal radiation, a belt of charged particles trapped by the planet's magnetic field, energetic enough to fry the electronics of any spacecraft that lingered too long. But the poles are quieter, and by flying over them, Juno could dip in close without swimming through the worst of that radiation bath. Close was the key. From a few thousand kilometers up, the instruments could do their work. The microwave radiometer could peer hundreds of kilometers into the atmosphere, measuring the faint glow of ammonia and water and hydrogen compressed by the weight of the gas above. The magnetometers could trace the shape of the magnetic field in detail, impossible from farther out, and the gravity science experiment could detect the subtle wobbles in Juno's trajectory caused by the uneven distribution of mass deep within the planet, wobbles measured in fractions of a millimeter per second, wobbles that would reveal what lay beneath the storms. The first data began to arrive in the autumn of 2016, and almost immediately it became clear that Jupiter was not what we had assumed. Consider for a moment what we thought we knew about the Great Red Spot before Juno arrived. It is the most famous storm in the solar system, a swirling anticyclone larger than the Earth, and we have been watching it in one form or another for more than 3 centuries. The astronomer Giovanni Cassini may have glimpsed it as early as 1665, though the records are uncertain. By the 19th century it was unmistakable, a prominent rusty oval drifting slowly westward along the southern edge of the planet's equatorial belt. Astronomers sketched it, measured it, named it. They assumed it was a storm, and they were right about that much. But they assumed too that it was a shallow thing, a disturbance in the upper atmosphere, perhaps a few tens of kilometers deep at most, a kind of vast hurricane resting on the invisible surface below. Juno's microwave radiometer told a different story. As the spacecraft swept over the Great Red Spot in the summer of 2017, its instruments peered not at the cloud tops but through them, measuring the faint thermal glow of the atmosphere at depths no telescope could reach, and what it found was a storm with roots. The Great Red Spot does not sit on a surface. There is no surface. The clouds we see are only the visible top of a column of churning gas that extends downward for hundreds of kilometers, far deeper than any storm on Earth, deep enough to swallow our entire atmosphere many times over. The temperature and composition change as you descend, the pressure mounting with every passing kilometre, but the storm continues, a vortex sinking into the dark, its lower reaches lit by nothing, stirred by forces we are only beginning to understand. It is not a hurricane resting on an ocean. It is more like a root pushing down into soil that has no bottom. And the Great Red Spot is not alone. The banded structure of Jupiter, those alternating stripes of cream and brown and rust that have delighted observers for centuries, turns out to be more than a surface pattern. The bands are the visible expression of jet streams, rivers of atmosphere flowing in alternating directions around the planet, and those jet streams do not fade away a few kilometers down. Juno's gravity measurements reveal that they extend thousands of kilometers into the interior, vast cylinders of moving gas reaching down toward the planet's heart. The winds we see at the cloud tops are only the outermost edge of a circulation that permeates a significant fraction of Jupiter's bulk. Imagine, if you can, standing on the deck of a ship and watching the waves roll past, assuming they are a surface phenomenon, a disturbance in the top few meters of the sea. And then imagine learning that those waves are not waves at all, but the visible tops of immense columns of water reaching all the way to the ocean floor, columns that move and shift and carry their motion into depths you cannot see. That is something like what Juno revealed about Jupiter's atmosphere. The storms are not on the planet. The storms are the planet, or at least a far greater part of it than anyone had supposed. But the surprises did not stop at the storms. When Juno reached the poles, it found something no one had predicted. Clusters of cyclones arranged in geometric patterns, holding their formation year after year like dancers frozen in a slow waltz. At the North Pole, 8 cyclones surrounded a single central vortex, their edges nearly touching. Their rotation locked together in a configuration that resembled an octagon. At the South Pole, the pattern was different. 5 cyclones around a central one, a pentagon of storms, each hundreds of kilometers across, each churning in the same direction, each maintaining its position as though held in place by invisible hands. Why don't they merge? On Earth, when 2 hurricanes draw close, They spiral around each other in a chaotic dance that often ends with one absorbing the other. But Jupiter's polar cyclones do not merge. They jostle, they shift, they wobble slightly in their orbits, but they hold their formation year after year, pass after pass. Something about the dynamics of the Jovian atmosphere, perhaps the planet's rapid rotation, perhaps the depth of the vortices, perhaps forces we have not yet identified, keeps them stable, pinned in place like marbles in a bowl. The images Juno returned were haunting. False colour portraits of the poles rendered in blues and oranges and whites, the cyclones swirling like cream stirred into coffee, their edges fractal and beautiful and utterly alien. Nothing in our experience of weather on Earth had prepared us for the sight. These were not storms driven by the heating of an ocean or the clash of air masses. They were structures embedded in an atmosphere thousands of kilometres deep, fed by energies we are still working to understand, stable on timescales that mock our brief human attention. And beneath the storms, deeper still, Juno began to trace the shape of something even stranger, a magnetic field unlike any we had expected. Planets with magnetic fields are not uncommon. Earth has one, generated by the churning motion of molten iron in its outer core, a dynamo that has protected our atmosphere from the solar wind for billions of years. Jupiter's magnetic field is the strongest of any planet in the solar system, strong enough to accelerate charged particles to tremendous energies, strong enough to shape a magnetosphere that stretches millions of kilometers into space, strong enough to make the Jovian radiation belts lethal to unprotected electronics. But before Juno, we assumed that magnetic field would be relatively simple in structure. A dipole like Earth's, two poles, and a smooth field connecting them, generated by currents flowing in a deep metallic core. Juno's magnetometers revealed something far more complicated. The field is lumpy. It is asymmetric. It is stronger in some places and weaker in others, and the pattern does not match what a simple dipole would produce. There are regions where the field is so intense that it punches through the surrounding structure like a searchlight, and regions where it fades to a relative whisper. The north and south magnetic poles are not directly opposite each other. The whole configuration suggests a dynamo that is not buried deep in a uniform core, but spread through a thicker layer, a region where hydrogen is squeezed so hard by the weight above that it begins to behave like a metal, conducting electricity, supporting the currents that generate the field. This is one of the strangest ideas in planetary science, and it deserves a moment of quiet attention. Deep inside Jupiter, the pressure is beyond anything we can replicate in a laboratory for more than a fleeting instant. Hydrogen, the lightest and simplest element, the gas that fills party balloons and burns in rocket engines, is compressed so thoroughly that its atoms are crushed together and their electrons break free, flowing through the material the way electrons flow through copper wire. The hydrogen becomes metallic, not a solid, not a liquid in the ordinary sense, but a state of matter that conducts electricity and heat with an efficiency that would seem impossible at the surface of our own world. Juno's measurements suggest that this metallic hydrogen region is not a thin shell wrapped around a dense core. It extends outward, mixing gradually with the molecular hydrogen above, its boundaries blurred and uncertain, and the currents flowing through it are not smooth and uniform but turbulent, irregular, shaped by the same deep convection that drives the storms at the surface. The magnetic field Juno mapped is a portrait of that convection, a record of the motion of material we cannot see, written in invisible lines of force. And at the very centre, where we expected to find the seed around which Jupiter formed, Juno found something even more unsettling in its implications. For decades, the leading theory of giant planet formation held that Jupiter began as a rocky core, a ball of heavy elements perhaps 10 times the mass of Earth, that gathered itself out of the dust and ice of the early solar system and then, once it grew massive enough, began to pull in hydrogen and helium from the surrounding disk. The core was the seed, the gas was the husk, and somewhere deep inside Jupiter that seed should still exist, compressed but intact, a dense heart of rock and metal buried beneath tens of thousands of kilometers of atmosphere. Juno's gravity measurements told a different story. The spacecraft's trajectory was tracked with such precision that scientists could detect the faint gravitational tug of mass concentrations deep within the planet. And what they found was not a compact core but a diffuse one, a region at the centre where heavy elements are indeed concentrated but smeared outward, mixed into the surrounding hydrogen, blurred like watercolours left out in the rain. The core is not a hard ball. It is a fuzzy gradient, a slow transition from the hydrogen-rich envelope to a region enriched in heavier stuff, but with no sharp boundary, no clean edge. What could have caused this? One possibility is that Jupiter's formation was more violent than we supposed. Perhaps early in its history a large object, a protoplanet, a world perhaps as massive as several Earths, collided with the young Jupiter and plunged into its depths, stirring the interior, mixing the core outward, diluting the seed that had gathered so patiently from the dust. Simulations suggest this is possible, that a collision of the right size and speed could produce exactly the kind of diffuse core Juno observed. If true, it means Jupiter carries within itself the record of a cataclysm, a scar from an impact that happened more than 4 billion years ago, an event so violent that it reshaped the interior of the largest planet in the solar system and left no visible trace on its surface. The storms we watch are utterly indifferent to that ancient violence. They churn on, unaware, painting the cloud tops in colours that tell us nothing of what lies beneath. Let us pause here for a moment and consider what Juno has shown us, because it is easy to lose the strangeness of it in the flood of detail. We thought Jupiter was a planet with an atmosphere. It turns out to be an atmosphere with no bottom, a world where the sky simply thickens as you descend, where the storms at the surface are only the outermost edge of a circulation that reaches thousands of kilometres into the interior, where the very idea of a surface is meaningless. We thought the Great Red Spot was a storm resting on something solid. It turns out to be a column of churning gas sinking into darkness, a vortex with roots that reach down farther than anything we have on Earth. We thought the poles would be quiet or chaotic or perhaps simply featureless. Instead, we found geometry. Cyclones arranged in octagons and pentagons, holding their formation for reasons we do not yet fully understand. And at the heart of it all, where we expected to find the seed around which Jupiter formed, we found instead a core that is not a core, a centre that is blurred and diffuse, perhaps stirred outward by an ancient collision, perhaps formed that way from the beginning, in either case unlike anything we had imagined. This is what it means to explore. Not to confirm what we already believe, but to have our beliefs gently unsettled, to discover that the universe is stranger and more interesting than we supposed, to find that a world we thought we knew has been hiding its true nature behind a painted sky. The mission was designed to last only a few years. Juno arrived in 2016, and the original plan called for it to complete its science objectives by 2018, after which it would be deliberately crashed into Jupiter's atmosphere to prevent any possibility of contaminating the potentially habitable moons with earthly microbes. But the spacecraft proved so healthy and the science so rich that the mission was extended and extended again, and as of this telling it is still there, still swinging over the poles every 53 days, still gathering data, still peering into the depths. And in those extended years, Juno has turned its attention not only to Jupiter itself but to the moons that circle it. The same 4 points of light that Galileo saw more than 4 centuries ago, now revealed as worlds in their own right, each with its own story, each with its own mysteries. But that is a tale for later. For now, let us stay with the planet itself, with the storms that have churned for centuries, with the roots that sink into darkness, with the core that is no core at all. There is more to understand, more to feel, more to hold in the mind as the night grows deeper. The Great Red Spot has been shrinking. This is something we have watched from Earth for more than a century, a slow contraction of the most famous storm in the solar system. In the late 19th century, the spot was large enough to swallow 3 Earths side by side. Today, it would fit only 1 1/4. No one knows for certain whether it will continue to shrink, whether it will one day vanish entirely, or whether it will stabilise at some smaller size and continue to churn for centuries more. Juno's observations have given us clues, measurements of the storm's depth, its wind speeds, its internal structure, but the future remains uncertain. What is certain is that the spot is not unique. Jupiter's atmosphere is full of storms, great and small, some lasting for decades, some flickering into existence and fading within months. The white ovals that drift through the southern hemisphere, the brown barges that appear and disappear in the equatorial belt, the festoons and plumes and turbulent wake regions that trail behind the larger vortices. All of these are part of a weather system so vast and so complex that we have only begun to map it. Juno sees them from above, tracing their structure with its microwave eyes, measuring their depth, their composition, their motion. And slowly, pass by pass, orbit by orbit, a picture is emerging of an atmosphere that is not a skin but a world unto itself, a churning ocean of gas with no shore, no bottom, no calm. Consider for a moment what it would be like to descend into that atmosphere. You begin above the cloud tops, in the thin upper haze where sunlight still filters through, where the temperature is cold enough that ammonia crystals float like snow in a winter sky. The light is golden, filtered by the haze, and the horizon curves away in all directions, banded in cream and rust and pale ochre. You are falling. As you descend, the sky above grows darker and the pressure begins to mount. The ammonia clouds thicken around you, then give way to layers of ammonium hydrosulfide, then to water clouds, if there are water clouds. Juno has detected water vapour, but the structure of the deeper cloud decks is still uncertain. The temperature rises with the pressure, the heat of compression warming the gas as you sink. 100 kilometres down, it is warm enough that you would not need a heater. 200 kilometres down, it is hot, and the light from the sun has faded to nothing. You are in darkness now, a darkness lit only by the faint glow of lightning flickering in the storms around you. Deeper still, the distinction between gas and liquid begins to blur. There is no surface to land on, no boundary to cross. The atmosphere simply grows thicker and thicker, denser and denser, until at some point, thousands of kilometres below the clouds, under pressures that would crush any structure we could build, the hydrogen becomes metallic, conducting electricity, supporting the currents that generate the magnetic field. And still, there is no surface, only a gradual transition, a slow change from the sky you know to something utterly alien, a state of matter that exists nowhere on Earth except in the fleeting instant of a laboratory experiment. And at the very centre, perhaps 20,000 kilometres down, perhaps more, the heavy elements are concentrated but not collected, mixed into the surrounding hydrogen like sugar dissolved in water, the remnant of a core that was never quite a core, or a core that was stirred outward by a violence we can only imagine. There is no stone to stand on. There is no solid ground. There is only the slow gradient of pressure and temperature and composition, climbing toward values that defy comprehension. This is what Juno has revealed. Not a planet with a surface and an atmosphere, but a planet that is all atmosphere. A world where the storms at the top are only the visible fringe of a structure that reaches all the way down to the heart. We have been watching Jupiter for 4 centuries, and we are only now beginning to understand what we were looking at. Spare a thought too for the people who built Juno and who have tended it across all these years. The mission was proposed in the early 2000s, one of many ideas competing for NASA's attention and funding. Its champion was a scientist named Scott Bolton, a man who had spent his career studying the giant planets, who believed that the key to understanding Jupiter lay not in its moons but in its interior, and who spent years persuading committees and review boards that the science was worth the cost. The spacecraft was built in Denver by a team of engineers who had to solve problems no one had solved before. How to shield electronics from Jupiter's brutal radiation, how to design solar panels that could generate power from a sun 5 times farther away than Earth's, how to build instruments sensitive enough to detect the faint whisper of water vapour hundreds of kilometres below the clouds. When Juno launched in 2011, some of those engineers had been working on the mission for more than a decade. When it arrived at Jupiter in 2016, some had spent half their careers waiting for this moment. And as the data began to flow, as the surprises accumulated, as the picture of Jupiter shifted and deepened and grew strange, they were there to receive it, to interpret it, to share it with the world. This is one of the quiet miracles of planetary exploration, easy to overlook in the flood of images and numbers, the human patience that makes it possible, the years of work that precede the years of discovery, the caretakers who tend to a machine across millions of kilometres of emptiness, listening to its faint signals, adjusting its course, keeping it alive far longer than it was ever designed to survive. Juno has been orbiting Jupiter for nearly a decade now, and every orbit it completes, every pass over the poles, every measurement of gravity and magnetism and composition is the fruit of that quiet tending. And so we return as we must to the storms. They are still there tonight, churning at the cloud tops, visible through any modest telescope, unchanged in their broad outlines since your great-grandparents were young. The Great Red Spot is rotating counterclockwise, one full turn every 6 days or so, a slow waltz that has continued without interruption for longer than any nation on Earth has existed. The bands are drifting east and west, carried by jet streams that reach down farther than anyone imagined. And at the poles, these cyclones are holding their formation, octagons and pentagons of spinning storms, waiting for the next pass of a small machine that has been watching them for years. What have we learned? We have learned that Jupiter is not what we thought. We have learned that its storms are roots, its atmosphere a world, its core a blur. We have learned that even a planet we have watched for 4 centuries can surprise us if we find a way to look beneath the surface. But the looking is not finished. Juno is still there, still gathering data, still sending its faint signals home across the vast gulf between Jupiter and Earth, and the questions that remain are as deep as the planet itself. How did Jupiter form? What happened in those first violent millions of years? Why do the polar cyclones hold their geometry? How deep does the metallic hydrogen extend, and what drives the dynamo that generates the magnetic field? Is there more water in the deep atmosphere than we have measured? And if so, what does that tell us about where Jupiter gathered its material? These are not questions that will be answered tonight, or even in the years remaining to Juno's mission. They are questions that will occupy scientists for decades, perhaps centuries. But the asking of them, the slow, patient work of discovery, is itself a kind of answer, a testament to the curiosity that sends small machines across the solar system, and to the wonder that keeps us watching a banded world through the long night. Let us sit for a long moment with the question of water, because it is one of the oldest questions we have ever asked about Jupiter, and one of the most stubbornly difficult to answer. When the first telescopes turned toward the giant planet in the 17th century, no one thought to ask whether Jupiter contained water. The question would have seemed almost meaningless. Water was something found in lakes and rivers and falling rain, not in the swirling bands of a distant world that appeared, through the eyepiece, as little more than a striped marble. But as our understanding of chemistry grew, as we learned that water is simply hydrogen and oxygen bound together, and that hydrogen is the most abundant element in the universe, the question began to seem not only reasonable but urgent. If Jupiter formed from the same disk of gas and dust that gave birth to the Sun and all the planets, it should contain water. The question was how much and where, and what that abundance might tell us about the circumstances of the planet's birth. The first serious attempt to measure Jupiter's water came not from Juno, but from an earlier visitor, a spacecraft called Galileo that arrived at the giant planet in 1995. Galileo carried with it a small probe, a capsule designed to plunge into Jupiter's atmosphere and take measurements as it fell. On December 7th of that year, the probe separated from its mothership, angled itself toward the cloud tops and began its descent. It was the first human-made object ever to enter the atmosphere of an outer planet, and its mission was to sample the air, measure the temperature and pressure, and radio its findings back to the orbiting spacecraft before the increasing heat and pressure crushed it into silence. The probe worked beautifully. For nearly an hour it fell through the atmosphere, its instruments recording everything they could detect, its transmitter sending a stream of data upward to Galileo, which relayed it across the solar system to the patient listeners on Earth. And then the data stopped as the probe descended beyond the depth where any machine could survive, and the atmosphere closed over it like water over a sinking stone. When scientists analysed the measurements, they found something unexpected. The probe had detected far less water than anyone had predicted. The deep atmosphere in the region the probe had sampled was drier than the driest desert on Earth. This was puzzling. Models of planetary formation suggested that Jupiter should be rich in water, perhaps several times richer than the Sun itself. But the probe had found almost none. For years, the discrepancy remained a mystery. Some scientists suggested that the probe had simply entered an unusual patch of atmosphere, a dry downdraft where the water had been wrung out by local weather patterns. Others wondered if the models were wrong, if Jupiter had formed in a way that left it genuinely water poor. The question mattered because water is a tracer, a clue to origins. The amount of water in Jupiter's atmosphere could tell us where in the early solar system the planet gathered its material, how it grew, what it swallowed on its way to becoming the giant we see today. Juno was designed, in part, to settle this question. Its microwave radiometer, the instrument that peers beneath the clouds, can detect the faint emission of water vapour at depths the Galileo probe never reached. And over the years of its mission, as it made pass after pass over different regions of the planet, it began to build a picture of Jupiter's water distribution that was far more complex than anyone had anticipated. The water, it turned out, is not evenly mixed. In some regions, the atmosphere is rich with it, in others it is scarce. The dry zone that the Galileo probe sampled appears to have been a genuine anomaly, a pocket of atmosphere where local dynamics had pushed the water away. But even the wetter regions contain less water than the simplest models predicted. The picture is not one of a planet uniformly enriched with water, but of a world where water is distributed unevenly, concentrated in some latitudes, depleted in others, stirred by circulation patterns that we're only beginning to understand. What does this tell us? It tells us that Jupiter's atmosphere is not a simple, well-mixed envelope of gas, but a dynamic system with structure and variation extending deep into the interior. It tells us that the process of planetary formation was messy, that the giant world accumulated its material in fits and starts, perhaps from different regions of the early solar system at different times, and it tells us that even after nearly a decade of observation, we do not yet have a complete answer to the question of how much water Jupiter contains. The measurement continues, orbit by orbit, pass by pass, the microwave radiometer peering downward into the dark, searching for the faint signal of vapour in the deep. Consider for a moment what it means to search for water inside a world like Jupiter. On Earth, water is everywhere, in the oceans, in the atmosphere, in the ground beneath our feet. We swim in it, drink it, watch it fall from the sky. But on Jupiter there is no surface, no ocean, no rain that reaches the ground. The water exists as vapour, suspended in an atmosphere that has no bottom, mixed with hydrogen and helium and ammonia, distributed according to pressures and temperatures and wind patterns that are unlike anything we experience in our daily lives. To measure it, Juno must look down through hundreds of kilometres of cloud, through layers of ammonia ice and ammonium hydrosulfide haze, through regions where the pressure is 10 times that of Earth's surface and the temperature is hundreds of degrees below zero, and detect the faint microwave glow of water molecules far below. It is a measurement made at the edge of what is possible, and the fact that we can make it at all is a testament to the patience and ingenuity of the engineers who designed the instrument and the scientists who interpret its signals. There is one more thing worth understanding about Jupiter's water, something that connects the question of abundance to the question of origins. In the early solar system, when the planets were forming, there was a boundary called the snow line, a distance from the young sun beyond which it was cold enough for water to freeze into solid ice. Inside the snow line, water existed mostly as vapour, difficult to capture and incorporate into growing planets. Outside the snow line, water could condense into ice, forming solid grains that could stick together, accumulate, and build the cores of giant planets. Jupiter is believed to have formed just beyond this boundary, in a region where ice was abundant, and its growth was fueled in part by the accretion of icy material from the surrounding disk. If this picture is correct, Jupiter should be enriched in water relative to the Sun, because it swept up vast quantities of ice during its formation. The Galileo probe's dry measurement cast doubt on this picture, but Juno's more comprehensive mapping has begun to restore it, at least in part. The water is there, just not uniformly distributed. The planet's history is written in the uneven mixing of its atmosphere, in the patterns of abundance and depletion that Juno has begun to trace, and the story that emerges is one of a world that grew through a process of accretion and differentiation, swallowing material from different parts of the disk, mixing some of it thoroughly, and leaving other regions stratified and distinct. It is worth pausing on the idea of stratification, because it connects to something deeper about Jupiter's interior. When we think of a gas giant, we might imagine a uniform ball of hydrogen and helium, the same from top to bottom, with perhaps a small rocky core at the centre. But Juno's measurements suggest something more complicated. The atmosphere is stratified by composition, with different layers containing different amounts of ammonia and water and other trace gases. The winds are stratified by depth, with the jet streams that drive the banded appearance extending thousands of kilometres down before fading into the slower moving deep interior. Even the core appears to be stratified in a sense, diluted and smeared outward rather than concentrated at the centre. Jupiter is not a uniform ball. It is a layered world with structure at every depth, and understanding that structure is the key to understanding how it formed and how it has evolved over the billions of years since. Return with me one more time to the magnetic field, because it is perhaps the strangest thing Juno has discovered, and it connects to the question of what lies at the very heart of the planet. A magnetic field, in the simplest terms, is generated by the motion of electrically conducting material. On Earth, the field is produced by the churning of liquid iron in the outer core, a process called a dynamo. The field is roughly dipolar, meaning it has two poles, like a bar magnet, aligned more or less with the planet's axis of rotation. It is what makes compasses work, what deflects charged particles from the sun, what creates the auroras that dance over the polar regions. Jupiter's magnetic field is far more powerful than Earth's, roughly 20,000 times stronger, generated not by liquid iron but by hydrogen, under such extreme pressure that it behaves like a metal. In the deep interior, where the pressure reaches millions of times that of Earth's atmosphere, hydrogen is squeezed so tightly that its electrons are freed from their atoms and can move freely, conducting electricity like a metal wire. This metallic hydrogen, churning and convecting under the influence of Jupiter's rapid rotation, generates the immense magnetic field that surrounds the planet. Before Juno arrived, scientists expected the field to be roughly dipolar, like Earth's, perhaps with some irregularities, but fundamentally symmetric. What they found was something quite different. The field is lopsided, stronger in some regions than others, with complex structures that do not fit the simple dipolar model. Near the equator, there is a region where the field is unusually weak, a kind of magnetic depression that suggests the dynamo is not operating uniformly throughout the metallic hydrogen layer. Near the poles, there are intense concentrations of magnetic flux, regions where the field lines are bundled tightly together, stronger than anywhere else on the planet. What does this mean? It suggests that the boundary between the metallic hydrogen and the molecular hydrogen above it is not sharp and clean but gradual and irregular. It suggests that there may be layers within the metallic region where the conductivity changes, where the convection patterns are different, where the dynamo operates according to rules we do not yet fully understand, and it hints at the possibility that the core itself, the dilute fuzzy core that Juno's gravity measurements revealed, may be influencing the field in ways that are difficult to model. The magnetic field is, in a sense, a window into the invisible interior. We cannot see through the clouds, we cannot send a probe to the centre, but we can measure the field from orbit and use it to infer something about the conditions far below. And what we infer is complexity, irregularity, a world that does not fit the simple models we constructed from a distance. Jupiter is teaching us, orbit by orbit, that giant planets are more intricate than we imagined, that their interiors are shaped by processes we are only beginning to glimpse. Picture, if you can, the journey downward from the cloud tops to the centre of the planet. It is a journey no spacecraft will ever make, no probe will ever survive, but we can imagine it, guided by the measurements Juno has gathered and the models scientists have built. You begin at the cloud tops, where the ammonia ice crystals catch the faint sunlight and scatter it in patterns of white and ochre and rust. The temperature here is cold, colder than any winter on Earth, and the pressure is roughly the same as at sea level on our world. You descend, and the light fades. Within a few hundred kilometres, the sun is gone, replaced by a perpetual darkness that will never lift. The clouds above are now only a memory, and the atmosphere around you is thickening, pressing in with increasing force. At a depth of perhaps 1,000 kilometres, the pressure has risen to 100 times that of Earth's surface, and the temperature has climbed to several hundred degrees. The hydrogen around you is no longer a gas in the familiar sense, but a dense, hot fluid, compressed beyond anything you could experience on a terrestrial world. The ammonia and water vapour are distributed unevenly, concentrated in some regions, depleted in others, stirred by convection currents that rise and fall over scales of hundreds of kilometres. You continue downward. The pressure climbs into the thousands of atmospheres, then the tens of thousands. The temperature rises to the point where the hydrogen begins to change its character, the electrons loosening from their atoms, the material becoming gradually more conductive. There is no sharp boundary, no line you cross from gas to liquid to metal. Instead, there is a slow transition, a gradient of increasing conductivity, until somewhere around 20,000 kilometers below the cloud tops you are surrounded by metallic hydrogen, a sea of shimmering fluid unlike anything found naturally on Earth. This is where the dynamo operates, where the churning of the metallic hydrogen generates the magnetic field that extends far out into space. The motions here are driven by heat from below, by the slow contraction of the planet and the residual warmth from its formation. The convection is not like the boiling of water in a pot, but a vast, slow circulation, rising and falling over timescales we can barely imagine. And yet it is this motion that creates the magnetic field that shields the moons from the worst of the solar wind, that makes Jupiter a world with its own invisible architecture extending millions of kilometers into space. You descend still further, and the pressure continues to rise. At some depth, perhaps halfway to the center, you begin to approach the region where the core should be. But there is no sharp boundary, no transition from metallic hydrogen to solid rock. Instead, there is a gradual enrichment of heavier elements, a smearing of the core material outward into the surrounding hydrogen, a blurring of the distinction between interior and envelope. The core, if we can still call it that, is not a hard kernel at the center, but a diffuse region of enhanced density, extending over a vast volume, more like a gradient than a boundary. What caused this? The answer is not certain, but one possibility is that early in Jupiter's history, before it had fully settled into its current state, it was struck by a massive impactor, perhaps another protoplanet, perhaps a giant embryo of a world that never got the chance to grow. The impact would have been cataclysmic, releasing enough energy to melt and mix the interior, to stir the core material outward into the hydrogen envelope, to blur the boundaries that would otherwise have been sharp. The fuzzy core we infer from Juno's gravity measurements may be the scar of that ancient collision, a memory of violence preserved in the structure of the planet for billions of years. Spare a thought too for the scale of this interior. The metallic hydrogen layer extends for tens of thousands of kilometers, a depth greater than the diameter of any rocky planet in our solar system. The pressures at the center reach hundreds of millions of times that of Earth's atmosphere, temperatures of tens of thousands of degrees, and yet the planet is not a furnace in the way we might imagine. It is radiating more heat than it receives from the sun, glowing faintly in the infrared with the warmth of its own slow contraction. But it is not a star, never came close to becoming one. Jupiter is massive, the most massive planet in our solar system, but it would need to be perhaps 80 times more massive to ignite hydrogen fusion in its core to become a small, dim star. It is a world that stopped just short of that threshold, a giant that grew as large as a planet can grow without crossing the line into stellar territory. This is part of what makes Jupiter so valuable to study. It is a laboratory for understanding the interiors of giant planets everywhere, including the thousands of giant planets we have now discovered orbiting other stars. Many of those worlds are larger than Jupiter, some smaller, some hotter, some colder. By understanding Jupiter's interior, its magnetic field, its composition, its layered structure, we gain insight into a whole class of worlds that dominate the galaxy. And Juno, circling patiently in its long elliptical orbit, is our most detailed probe of that interior, gathering data that will inform our understanding of giant planets for decades to come. And we cannot leave this story without returning to the cyclones, the strange geometric storms at the poles that have captivated scientists since Juno first observed them. They remain, as of tonight, one of the most beautiful and perplexing features the spacecraft has revealed. At the North Pole, a central cyclone is surrounded by 8 others, arranged in a nearly perfect octagon. At the South Pole, a similar arrangement exists with 5 surrounding cyclones, forming a pentagon. Each cyclone is enormous, hundreds of kilometers across, with wind speeds reaching hundreds of kilometers per hour. And they have held their formation for years, drifting slightly, adjusting their positions but never merging, never drifting apart as though held in place by some invisible architecture. Why do they not merge? On Earth, when 2 hurricanes approach each other, they often spiral together and combine into a single larger storm, a process called the Fujiwara effect. But Jupiter's polar cyclones resist this tendency. They approach, they jostle, they adjust, but they remain separate, each maintaining its identity within the larger geometric pattern. Something about the dynamics of Jupiter's polar regions, The rotation of the planet, the properties of the atmosphere, the energy flowing up from below, creates conditions where these storms can coexist in stable configurations rather than collapsing into chaos. The geometry itself is significant. Octagons and pentagons are not random arrangements. They are the result of specific dynamical constraints, of balance between the forces that push the cyclones apart and the forces that hold them together. Scientists have built models, run simulations, tried to reproduce the patterns in computer experiments. Some have succeeded, at least approximately, by tuning the parameters of their models to match the conditions on Jupiter. But the full explanation remains elusive. We know that the cyclones exist, we know their shapes and sizes and wind speeds, but we do not yet fully understand why they arrange themselves as they do, or how long they will maintain their geometry before some perturbation disrupts the pattern. It is worth trying, just once, to feel what it might be like to stand within one of these storms. Imagine yourself at the edge of a polar cyclone, looking inward toward its dark centre. The wind is screaming past at hundreds of kilometers per hour, a force beyond anything you have experienced on Earth. The clouds are towering walls of ammonia ice and hydrocarbon haze, rising kilometers into the air, lit from below by the faint glow of the planet's internal heat. You cannot see the sun. At these latitudes, at these depths, there is only darkness and the faint luminescence of chemical reactions in the clouds. And surrounding you, just beyond the edge of your storm, are 7 or 8 others, each a mirror of your own, each spinning counterclockwise in a dance that has continued for years without interruption. This is the reality of Jupiter's poles, a reality that no human eye has ever seen directly, that exists only in the data returned by a small spacecraft and the images constructed from that data by patient scientists on Earth. It is a reality that challenges our intuitions about weather and storms, about order and chaos, about the behaviour of atmospheres on worlds far larger and stranger than our own. There is a smaller, quieter story woven through all of this, one that is easy to miss amid the grandeur of the storms and the depths of the interior. It is the story of Juno itself, a machine built by human hands, launched across hundreds of millions of kilometers, kept alive and functioning for years beyond its original mission. The spacecraft is, in a sense, an extension of ourselves, a way of seeing and measuring and understanding that would otherwise be impossible. And like all machines, it is finite, vulnerable, subject to the wearing effects of time and radiation. Jupiter's radiation environment is among the harshest in the solar system. The planet's immense magnetic field traps charge particles from the solar wind and accelerates them to enormous energies, creating belts of radiation that would be lethal to any unprotected electronics. Juno was designed with this in mind, its sensitive instruments protected inside a titanium vault, its orbit chosen to minimize the time spent in the most intense radiation zones. But even with these precautions, the spacecraft accumulates damage with every pass, its components gradually degrading under the relentless bombardment. The mission was originally planned to last for about 5 years. It has now been operating for nearly a decade, far exceeding its design lifetime, a testament to the skill of its builders and the care of its operators. But nothing lasts forever. Eventually the radiation will take its toll, the instruments will fail, the communication links will falter, Juno will fall silent, and its orbit will slowly decay until the spacecraft plunges into Jupiter's atmosphere and is consumed, adding a tiny increment to the mass of the giant world it spent so long studying. That day is not yet here. Juno is still active, still gathering data, still sending its faint signals home. But it is a reminder, a gentle one, that all our missions of exploration are finite, that the knowledge they gather is hard-won and precious, that the window of opportunity for discovery is always closing, even as new windows open elsewhere. The spacecraft orbiting Jupiter tonight is doing work that no future mission will repeat in quite the same way. Its measurements are unique, its perspective irreplaceable, and the scientists who receive its data, who analyze its signals, who build their models and test their theories, are working against time, trying to extract every last insight before the machine falls silent. This is the nature of planetary exploration, the bittersweet rhythm of discovery and loss. We send our machines outward, we tend to them for as long as we can, we gather what they find and then we let them go. And what remains, after the machine is gone, is the knowledge, the understanding we gained, the questions we answered, the new questions we learned to ask. Juno will not last forever, but the picture of Jupiter it has revealed will endure, will shape our understanding for generations, will be refined and extended by future missions and future generations of scientists. The work does not end when the spacecraft falls silent. It continues in the papers and the models and the textbooks, in the slow accumulation of understanding that is the true legacy of exploration. And so, tonight, as you settle into rest, Jupiter is still out there, visible as a bright point of light if you step outside and look toward the sky. The storms are still churning, the cyclones are still spinning at the poles, the deep interior is still circulating in its slow, patient way. And Juno is still circling, still watching, still listening to the faint whispers of a world that has kept its secrets for 4.5 billion years. The planet does not know it is being watched. It has no awareness of the small machine that swings past every few weeks, no sense of the instruments pointed at its clouds, no understanding of the signals that pulse outward toward a distant, tiny world. Jupiter simply exists, as it has existed since the solar system was young, vast and turbulent and indifferent to the curiosity of creatures that arose billions of years after its formation. And yet there is something almost intimate about the relationship that has developed over these years of observation, a kind of one-sided conversation between a machine and a world, between the questions we ask and the answers the giant planet offers up in its own inscrutable language of magnetic fields and thermal emissions and the subtle wobbles of its gravitational pull. Consider for a moment the nature of the data that flows back to Earth from Jupiter's vicinity. It is not a photograph in any ordinary sense, not a simple image captured by a camera and transmitted home. The information Juno gathers is far more abstract, far more deeply encoded. It includes measurements of the magnetic field at different altitudes and latitudes, recorded as the spacecraft swoops through regions of varying intensity. It includes the precise tracking of Juno's velocity, detected through the tiny Doppler shifts in its radio signal, shifts that reveal the gravitational tugs of mass concentrations deep beneath the clouds. It includes spectra of infrared radiation, passed into wavelengths that correspond to different molecules and different temperatures and different depths in the atmosphere. It includes counts of charged particles, records of plasma waves, measurements of the aurora's glow in ultraviolet light that no human eye could ever see directly. All of this arrives at Earth as a stream of ones and zeros, faint and easily lost in the noise, captured by enormous antennas and decoded by computers, and then, finally examined by human minds trying to make sense of what the numbers mean. The process is slow and painstaking. A single gravity pass might yield data that takes months or years to fully analyze, to compare against theoretical models, to check and recheck for errors and artifacts. The scientists who work with Juno's data are engaged in a kind of translation, converting the abstract signals into maps and graphs and eventually into understanding. They are building, piece by piece, a portrait of a world that no human will ever visit in person, a world known only through the proxy of instruments and mathematics and careful, patient thought. And what emerges from this translation is a Jupiter that would have astonished the observers of earlier centuries, a Jupiter that challenges even the expectations of the scientists who designed the mission. The planet we thought we knew turns out to be layered in ways we had not imagined, dynamic in ways we had not suspected, structured by processes that operate on scales and timescales almost beyond human comprehension. The storms we see in visible light are only the outermost expression of something far deeper and more complex, like the whitecaps on an ocean whose true currents flow far beneath the surface. It is worth pausing on the question of what we mean when we speak of Jupiter's atmosphere. On Earth, the atmosphere is a relatively thin shell of gas surrounding a solid surface, a layer that extends perhaps 100 kilometers before giving way to the vacuum of space. We can stand on the ground and look up at the sky and draw a clear distinction between the world beneath our feet and the air that surrounds us. Jupiter offers no such clarity. There is no surface to stand upon, no boundary between atmosphere and interior. The gas simply grows denser and denser as you descend, the pressure mounting with every kilometre, until eventually the gas becomes so compressed that it behaves like a liquid, and then, deeper still, like something stranger, a fluid state that defies easy categorization. The atmosphere and the interior are not separate things, but a continuum, a gradual transition from the wispy upper clouds to the crushing depths where hydrogen itself takes on properties we can barely reproduce in laboratories on Earth. Juno's measurements have allowed scientists to trace this transition with unprecedented precision. The spacecraft's gravity data, in particular, has revealed how mass is distributed within the planet, how the density changes with depth, where the boundaries lie between different layers and states. And what emerges is a picture of a world that is, in a sense, mostly atmosphere. A planet-sized ball of gas and fluid with no hard centre, no rocky surface waiting to be discovered beneath the clouds. The core, such as it is, appears to be a diffuse region rather than a compact sphere, a zone where heavier elements are mixed with the surrounding hydrogen and helium, rather than concentrated in a neat, dense ball. This was one of Juno's most surprising findings, and it has forced scientists to rethink the story of how Jupiter formed and how it has evolved over the eons. The old picture was relatively simple. Jupiter, like the other giant planets, was thought to have begun with a solid core, a rocky, icy body perhaps 10 or 20 times the mass of Earth, which accumulated in the early solar system from the debris of the protoplanetary disk. This core then gravitationally attracted the surrounding gas, sweeping up hydrogen and helium in vast quantities until it had grown to its present enormous size. The core would remain at the centre, distinct and solid, a kernel of rock and ice surrounded by layer upon layer of gas. But Juno's gravity data suggests something different, something more complex. The core appears to be diluted, its heavy elements spread outward into the surrounding envelope, as though something had stirred the interior, mixing the core material with the hydrogen above. One possibility is that early in Jupiter's history, another large body, a protoplanet perhaps the size of Uranus, collided with the young giant and plunged into its interior, disrupting the core and scattering its material outward. Such a collision would have been cataclysmic, an event of unimaginable violence, and yet it would have left few traces on the surface, which has long since been erased by the churning of the atmosphere and the slow circulation of the interior. This is one of the humbling aspects of planetary science. The events that shaped a world billions of years ago leave only subtle signatures, faint echoes encoded in the distribution of mass or the composition of the atmosphere. Deciphering these signatures requires not just careful measurement, but also a willingness to entertain possibilities that might seem outlandish at first glance. The idea of a giant impact on Jupiter, a collision that reshaped its very core, is exactly the kind of hypothesis that emerges when the data refuses to fit the simpler models. It is a reminder that the solar system's history was violent and chaotic, that the worlds we see today are the survivors of a long process of accretion and collision, and that even the largest and most stable-seeming planet carries scars from its turbulent youth. Spare a thought, too, for the depth at which hydrogen ceases to behave like any gas we know and becomes something truly alien. On Earth, hydrogen is the lightest and simplest of elements, a colourless, odourless gas that rises in any atmosphere, the stuff of balloons and stars. But under the pressures found deep within Jupiter, hydrogen is forced into states that we can only study in the most extreme laboratory conditions. At depths of perhaps 20,000 kilometres, the pressure becomes so great that the hydrogen molecules are crushed apart, their electrons liberated to flow freely, and the gas becomes a metallic liquid, capable of conducting electricity like a wire. This layer of metallic hydrogen is believed to be the source of Jupiter's immense magnetic field. The currents flowing within it generating the dynamo that creates the magnetosphere, extending millions of kilometres into space. Juno cannot observe this layer directly. No instrument we possess can peer through the thousands of kilometres of overlying atmosphere to see the metallic hydrogen beneath. But the spacecraft's magnetic field measurements, combined with the gravity data, allow scientists to infer the properties of this hidden region, to build models of how the currents flow and how the field is generated. And what these models reveal is a magnetic field far more complex than Earth's. A field that is not centered on the planet's rotation axis, not symmetric, not simple. The field is strongest in the northern hemisphere and weaker in the south, with regions of intense flux and regions of relative calm, a patchwork that hints at the complicated motions of the metallic hydrogen far below. The great blue auroras that glow at Jupiter's poles, visible to Juno's ultraviolet cameras, are shaped by this field, their patterns reflecting the invisible geometry of currents and loops that extend deep into the planet's interior. Return with me, one more time, to the surface we can see, to the cloud tops where the colours and storms play out in patterns that have fascinated observers for centuries. The Great Red Spot has already entered our story, that ancient storm whose roots extend hundreds of kilometres into the atmosphere. But it's only one of many, only the most famous member of a family of vortices that dot Jupiter's face like the spots on a marble. Some of these storms are white, pale ovals that drift along the edges of the belts and zones. Others are brown, regions of descending air where the clouds thin and we glimpse slightly deeper, warmer layers beneath. Some are transient, lasting only months or years before being torn apart by the shearing winds. Others persist for decades, perhaps longer, maintaining their structure against the turbulent flow that surrounds them. Juno's close passes have revealed the three-dimensional structure of some of these storms, their roots and their depths, the way they interact with the surrounding atmosphere. The spacecraft's microwave radiometer, in particular, has proven invaluable for this work, peering beneath the visible cloud layers to map the distribution of ammonia and water vapour at different depths. What emerges is a picture of storms as deeply anchored phenomena, not shallow whirlpools spinning on the surface, but massive columns of rotating gas extending far down into the atmosphere. The Great Red Spot, for all its fame, is part of a continuum, one expression of a planet where the boundary between weather and interior circulation is blurred beyond recognition. And then there are the poles, those strange and beautiful regions where the cyclones cluster in their geometric arrangements. The North Polar Cluster, with its 8 cyclones surrounding a central ninth, and the South Polar Cluster, with its 5 or 6, have remained remarkably stable over the years of Juno's observations. The cyclones drift and shift, their positions changing slightly, but the overall pattern endures, the polygonal arrangement maintained by some balance of forces that scientists are still working to understand. Similar patterns have been observed in laboratory experiments with rotating fluids, suggesting that the geometry emerges naturally from the physics of vortices interacting in a rotating frame. But Jupiter's poles are far more complex than any laboratory tank, their cyclones far larger and more energetic, and the details of how the patterns form and persist remain an active area of research. Picture, if you can, what it would be like to approach one of these polar cyclones, to descend through the upper haze and into the swirling wall of clouds that marks the storm's edge. The cyclone might be 1,000 kilometres across, large enough to swallow a small country, its winds spiralling inward at hundreds of kilometres per hour. Lightning might flicker in the depths, brief flashes illuminating the churning ammonia, ice and water clouds far below. The colours would shift as you descended, from the pale haze of the upper atmosphere to the deeper reds and browns of the cloud layers beneath, and the sound, if sound could carry in that thin and alien air, would be the roar of wind beyond anything Earth has ever known. A continuous howl of gas rushing past at speeds that would strip the paint from any vessel we could build. But of course, no vessel could survive such a descent. The pressures would crush any probe long before it reached the depths where the most interesting physics occurs. The one spacecraft we ever sent into Jupiter's atmosphere, the Galileo probe in 1995, survived for less than an hour, transmitting data as it fell through the upper layers before the mounting pressure and heat destroyed it. It reached a depth of perhaps 150 kilometres, a tiny fraction of the planet's radius, before it fell silent. What it found was a world drier than expected, with less water vapour than models had predicted, a puzzle that scientists debated for years afterward. Some suggested that the probe had simply entered an unusually dry region, a localised downdraft where the air was depleted of moisture. Others proposed more exotic explanations. The question remains partially open even now, one of many mysteries that Juno's orbital observations are helping to address, if not fully resolve. There is one more thing worth understanding about the way Juno studies Jupiter, a subtlety that speaks to the ingenuity of the mission's designers. The spacecraft does not simply point its instruments at the planet and record what it sees. Instead, it uses its own motion, its trajectory through Jupiter's gravitational and magnetic fields, as a measuring tool. By tracking the tiny changes in Juno's velocity as it swings past the planet, scientists can map the gravitational field with exquisite precision, inferring the distribution of mass beneath the clouds. By measuring the magnetic field at many different points along the orbit, they can build a three-dimensional picture of the field structure, tracing its sources deep in the metallic hydrogen layer. The spacecraft itself becomes an instrument, its path through space a probe of the invisible forces that shape Jupiter's interior. This technique, called radio science, has been used on many planetary missions, but Juno has pushed it to new levels of precision. The tracking is so accurate that scientists can detect the gravitational effects of individual storms, the subtle tugs exerted by the mass anomalies associated with the Great Red Spot or the polar cyclones. These measurements have confirmed that the storms are not shallow features but deep-rooted structures, their mass extending far below the visible cloud tops. It is a remarkable achievement, the ability to weigh a storm from hundreds of millions of kilometers away, to sense its depth through the faint wobbles it imparts to a passing spacecraft. And so the picture builds, layer upon layer, observation upon observation. Jupiter emerges not as the simple striped giant of our childhood memories, but as a world of astonishing complexity, a planet where the atmosphere and interior are one continuous system, where storms extend thousands of kilometers into the deep, where the magnetic field is twisted and asymmetric, where the core itself may have been disrupted by ancient violence. The questions we asked at the beginning of this journey, the questions about what lies beneath the endless storms, have been answered in part and replaced by new questions, deeper and more subtle. Why do the polar cyclones arrange themselves in such stable patterns? What drives the deep winds that extend so far below the cloud tops? How did the core become diluted, and what does this tell us about Jupiter's formation? What other surprises await in the data that Juno continues to gather? Let us sit for a long moment with the sheer scale of what we are contemplating. Jupiter is more than a planet in the ordinary sense. It is a failed star, a body that accumulated enough mass to dominate its region of the solar system, but not quite enough to ignite the nuclear fires that burn in the Sun's core. If Jupiter were perhaps 70 or 80 times more massive, it would have crossed that threshold and we would live in a binary star system, two suns in the sky, a very different Earth if Earth existed at all. As it is, Jupiter radiates more energy than it receives from the Sun, a slow leakage of primordial heat left over from its formation and contraction. The planet is still cooling, still settling, still slowly shrinking by a fraction of a centimetre each year, its interior releasing the heat of its birth over billions of years. This internal heat drives much of what Juno observes. The convection that carries heat from the deep interior to the cloud tops, the circulation patterns that create the belts and zones, the storms that churn and persist for centuries, all are powered by the slow release of Jupiter's ancient warmth. The planet is, in a sense, a heat engine, a vast machine converting thermal energy into motion, and the patterns we see on the surface are the visible expression of that engine's workings. Understanding those patterns, tracing their origins, connecting the surface weather to the deep interior, this is the work that Juno was designed to do, and it is work that will continue for as long as the spacecraft remains functional, and in the analysis of its data for decades after it falls silent. It is worth trying, just once, to feel the immensity of the time that Jupiter has endured. 4.5 billion years, a number so large that it resists comprehension. When Jupiter formed, the Sun was young and slightly dimmer than it is today, and the Earth did not yet exist in its present form. The first single-celled life on our planet would not appear for hundreds of millions of years. The dinosaurs, the ice ages, the rise of human civilization, all of it took place in the blink of an eye compared to Jupiter's long existence. And through all of that time, the storms have churned, the cyclones have spun, the Great Red Spot or its predecessors have marred the face of the giant planet with their crimson stain. The winds that blow tonight have blown for longer than life has existed on Earth, and they will likely continue long after whatever future awaits us has played itself out. There is a smaller, quieter story woven through all of this, the story of the people who have devoted their careers to understanding Jupiter, who have spent years or decades working with Juno's data, who have argued and collaborated and published and revised their models in the slow, incremental way that science advances. Some of them began this work when they were young, when the mission was still being designed, and they have grown older alongside it, their understanding of Jupiter deepening even as the spacecraft they built accumulates its radiation damage in the harsh Jovian environment. They know that their time with Juno is limited, that the data flowing in today is precious precisely because it will not flow forever. And so they work with urgency and care, extracting every last photon of insight from the signals that arrive at the deep space antennas, publishing their findings, training the next generation of scientists who will carry the work forward when they are gone. This is the human dimension of the mission, the part that is easy to overlook when we focus on the grandeur of Jupiter itself. The planet does not care about the papers published in scientific journals, does not know that its secrets are being revealed to creatures on a world 1 billion kilometers away. But we care. We care deeply, because understanding the universe is one of the things that makes us human, one of the ways we assert our presence in a cosmos that is mostly empty and cold and indifferent. Juno is our emissary, our extension, our way of reaching across the void to touch something vast and ancient and utterly unlike ourselves. And the knowledge it brings back is not just data but a kind of connection, a thread linking our small world to the larger story of the solar system. And so, as the night deepens and sleep draws nearer, Jupiter continues its ancient dance, the storms churning, the cyclones spinning, the deep interior circulating in its slow, patient rhythm. Juno continues its orbit, swinging close and then retreating, gathering data with every pass, its instruments still functioning despite the years of radiation exposure. The scientists continue their work, poring over the numbers, refining their models, asking new questions as old ones find their answers, and you, listening to this story in the quiet of the evening, are part of it too, connected by curiosity to a world you will never visit, a world that has kept its secrets for eons and is only now, slowly, beginning to share them. The storms are not the whole story, and neither is the core and neither is the magnetic field. The whole story is the weaving together of all these threads, the recognition that Jupiter is a single, unified system, atmosphere and interior and magnetosphere all connected, all influencing each other, all part of one vast, churning, radiant world. Juno has given us pieces of that story, pieces that we are still assembling, still learning to read. And the picture that emerges, incomplete as it remains, is more beautiful and more strange than anything we imagined when we first turned our telescopes toward that bright wandering star so many centuries ago. The magnetosphere of Jupiter is a cathedral built of invisible force, a structure so vast that if human eyes could perceive it, it would appear larger in our night sky than the full moon, stretching outward from the planet in an elongated bubble that extends millions of kilometers into the darkness of space. It is the largest structure in our solar system, apart from the heliosphere itself, the great bubble blown by the solar wind that encloses all the planets in its embrace. And Juno, passing through this magnetic domain again and again, has revealed it to be even stranger than the models predicted, a realm of energies and currents that defy simple description. The source of this magnetic field lies deep within the planet, in that ocean of metallic hydrogen where pressures strip electrons from their atoms and allow them to flow like water. The currents moving through this conducting sea generate the magnetic field the way currents in the molten iron of Earth's core generate ours, but the scale is almost beyond comparison. Jupiter's magnetic field is nearly 20,000 times stronger than Earth's, strong enough to accelerate particles to tremendous energies, strong enough to create radiation belts that would be lethal to any unshielded human within minutes. Juno was designed to survive in this environment, its most sensitive electronics tucked inside a titanium vault the size of a car trunk, shielded from the worst of the radiation by nearly 2 centimeters of metal. Even so, the spacecraft accumulates damage with every close pass, its systems degrading slowly under the constant bombardment of energetic particles. What Juno discovered about the magnetic field surprised the scientists who had spent years modelling it. They expected something relatively symmetrical, something that could be described with the same mathematical tools used to describe Earth's field. Instead, they found a field that was lopsided, concentrated in the northern hemisphere, weaker and more diffuse in the south. The magnetic equator did not align with the geographic equator but wandered significantly, and there were regions where the field was so intense and localized that they could only be explained by currents flowing surprisingly close to the surface of the planet, perhaps in that transition zone where metallic hydrogen gives way to the molecular gas above. The field was also more complex than expected, with higher-order features that suggested turbulent flows in the deep interior, eddies and swirls in the conducting ocean that left their fingerprints in the magnetic geometry. This asymmetry has implications for everything from the radiation belts to the aurora, those shimmering curtains of light that dance at Jupiter's poles just as they dance at Earth's. But Jupiter's aurora are not gentle displays of green and purple. They are among the most energetic phenomena in the solar system, powered by millions of amperes of current flowing between the planet and its moons, particularly Io, that volcanic world whose eruption sends sulfur and oxygen streaming into space to be caught by the magnetic field and swept into a donut-shaped torus encircling Jupiter. The interactions are complex beyond easy description, a dance of charged particles and magnetic flux tubes that Juno has mapped in unprecedented detail, revealing how energy flows from the deep interior of the planet outward into space, how the moons and the magnetosphere and the solar wind all interact in ways that no previous mission could fully characterize. Consider for a moment the scale of what Juno has accomplished in this magnetic mapping. The spacecraft carries a magnetometer, an instrument designed to measure the strength and direction of magnetic fields with exquisite precision. As Juno swings close to Jupiter on each perigove pass, skimming just a few thousand kilometers above the cloud tops before retreating to the distant reaches of its orbit, the magnetometer samples the field at point after point along its trajectory. Over the course of dozens of such passes, spanning years of patient measurement, these samples have been assembled into a three-dimensional model of Jupiter's magnetic field, a map of invisible force that extends from the cloud tops down into the conducting interior and outward into space. The resolution of this map improves with each pass, as more data points are added to the picture, as regions that were only glimpsed on earlier orbits are sampled again and again from different angles. The picture that emerges is one of a planet whose interior is far more dynamic than the calm exterior might suggest. The magnetic field is not static but evolving, changing on timescales of years as the currents in the deep interior shift and flow. Some researchers have suggested that they can detect secular variation in the field, the slow drift of magnetic features that on Earth take centuries but on Jupiter might unfold more rapidly, driven by the faster rotation and the different dynamics of the metallic hydrogen ocean. If confirmed, this would mean that Jupiter's magnetic field is a living thing, constantly reshaping itself in response to the flows beneath the clouds, a snapshot of processes that have been ongoing since the planet formed and that will continue for billions of years to come. Spare a thought too for the moons that orbit within this magnetic embrace, worlds that have their own stories to tell, their own secrets that Juno has glimpsed in passing. Ganymede, the largest moon in the solar system, possesses its own magnetic field, the only moon known to do so, and Juno has flown close enough to map the boundary where Ganymede's small field meets Jupiter's vast one, a region of complex interactions that scientists are still working to understand. Europa, that ice-covered world with its hidden ocean, lies within the radiation belts where charged particles bombard its surface, potentially creating chemistry that could be relevant to the question of habitability. Io, that tortured volcanic world, is the source of much of the plasma that fills the magnetosphere, its eruptions feeding material into the system that is then energized and transported by Jupiter's rotating magnetic field. Juno was not designed as a moon mission, its primary focus always being Jupiter itself, but the spacecraft has seized opportunities to study these worlds when its orbit brings it close. The images of Ganymede's cratered surface, of Europa's fractured ice, of Io's volcanic plumes have added to the growing archive of data about the Jovian system, pieces of a larger puzzle that future missions will explore in greater detail. For now, these glimpses are tantalizing hints of the complexity that awaits further investigation, reminders that Jupiter is not a solitary giant but the center of a miniature planetary system, a collection of worlds bound together by gravity and magnetism into a single interacting whole. Return with me, one more time, to the spacecraft itself, that small creation of human hands spinning slowly against the backdrop of stars. Juno carries 9 scientific instruments, each designed to answer specific questions about Jupiter's composition, structure, and environment. The microwave radiometer peers through the clouds to sense the temperature and ammonia content of the atmosphere at different depths. The gravity science experiment uses the spacecraft's radio signal to detect the tiny accelerations caused by variations in Jupiter's internal density. The infrared mapper captures the heat rising from below the cloud tops, revealing the structure of storms and the temperature differences between zones and belts. The ultraviolet spectrograph studies the aurora, the energetic particles that rain down along magnetic field lines to create those brilliant polar displays. Each instrument contributes its own strand to the tapestry of understanding, each data set revealing something that the others cannot see. The spacecraft itself has become a kind of veteran explorer, its solar panels still generating power after years in the harsh Jovian environment, its reaction wheels still capable of pointing the instruments with precision, its main antenna still sending its data across the enormous gulf of space to the antennas waiting on Earth. It has survived longer than some expected, its mission extended multiple times as it continued to function and continued to return valuable data. The original mission plan called for Juno to make 35 orbits of Jupiter before being deliberately deorbited into the planet's atmosphere, a fiery end designed to prevent any possibility of contaminating the potentially habitable moons with earthly microbes. That end has been postponed as the spacecraft has proven more durable than anticipated. Its mission expanded to include flybys of the moons and extended observations of the polar regions. Picture, if you can, the view from Juno's perspective as it approaches perigove, the closest point in its orbit, the moment when Jupiter fills the entire sky. The cloud tops rush past below at speeds that would be terrifying if there were a human pilot to feel fear. The radiation counters spike as the spacecraft plunges through the innermost radiation belts, regions where the particle flux is so intense that even Juno's shielding cannot block it all. The instruments collect data as fast as they can, storing it in the spacecraft's memory for transmission later, when the spacecraft has climbed back to the quiet outer reaches of its orbit and has time to slowly relay its treasures to Earth. This happens again and again, orbit after orbit, a rhythm that has continued for years and will continue for several more until the mission finally ends. It is worth pausing on the sheer improbability of this endeavour, the chain of decisions and discoveries and engineering triumphs that made it possible. Someone had to imagine that we could build a spacecraft capable of surviving Jupiter's radiation environment. Someone had to design the solar panels that could generate enough power so far from the Sun. Someone had to develop the algorithms that would allow the spacecraft to navigate and point itself with precision over 1 billion kilometers from any human controller. Each of these challenges was daunting, and each was overcome through persistence and ingenuity, and the collective effort of thousands of people working over many years. The result is a machine that represents some of the best that human beings are capable of producing, a testament to our curiosity and our skill. And what of the future, the time after Juno has fallen silent, after its instruments have failed and its transmitter has gone dark and the spacecraft itself has become one more piece of debris orbiting the giant planet? The data it has collected will outlive the machine that collected it, stored in archives on Earth where scientists can study it for decades to come. New questions will emerge as new analytical techniques are developed, and researchers will return to the Juno dataset again and again, finding answers that the original mission designers never thought to ask about. This is the nature of scientific data, that it continues to yield insights long after the instrument that gathered it has ceased to function. The legacy of Juno will be measured not just in the discoveries announced during its operational lifetime, but in all the understanding that flows from its measurements in the years and centuries ahead. There is one more thing worth understanding about what Juno has found, something that connects all the individual discoveries into a larger whole. Jupiter is a world in constant transformation, its atmosphere mixing and churning, its interior convecting and circulating, its magnetic field evolving and reshaping itself. Nothing about the planet is static. The zones and belts we see through our telescopes are not permanent features but the visible expression of processes that operate on timescales from hours to centuries. The Great Red Spot, ancient as it seems, is a transient phenomenon on geological timescales, a storm that formed at some point in the past and will dissipate at some point in the future, perhaps sooner than we expect given the shrinking that has been observed over the past century. Even the deep interior, that realm of metallic hydrogen and dissolved rock, is not frozen in place but participating in the slow dance of convection that transports heat from the centre outward. This dynamism is part of what makes Jupiter so fascinating to study. It is a laboratory for understanding fluid dynamics and magneto-hydrodynamics and planetary formation, a natural experiment on a scale that no Earthbound laboratory could ever replicate. The discoveries Juno has made about the depth of the winds, the structure of the polar cyclones, the complexity of the magnetic field, and the nature of the core all contribute to our understanding of how planets work in general, not just how this particular planet works. The same physics that operates on Jupiter operates on the gas giants of other solar systems, worlds we can observe only as points of light but whose properties we can infer by understanding their nearest analogue. Let us sit for a long moment with the quiet reality of Jupiter's indifference. The planet does not know it is being studied. The storms do not care that we have measured their depths. The magnetic field continues its complex dance regardless of whether anyone understands it. In a universe that is mostly empty and mostly cold and mostly devoid of anything that could appreciate its grandeur, Jupiter simply exists, doing what it has always done, being what it has always been. Our understanding adds nothing to the planet and takes nothing away, but it adds something to us. It expands the boundaries of the known, pushes back the darkness of ignorance by one small margin, connects us to something larger than ourselves. The spacecraft named Juno continues its work as you listen to these words, assuming the mission has not ended in the time between when this was written and when you hear it. It is out there tonight, orbiting the giant planet, its instruments sampling the radiation environment, its cameras perhaps capturing one more image of the swirling clouds, its antenna perhaps already turned toward Earth to transmit the latest batch of data. The distance is so great that even light takes more than half an hour to cross it, so what we receive on Earth is always a message from the past, news of what Juno observed 40 or 50 minutes ago. There is something poignant in this delay, this reminder that even our fastest signals are slow compared to the vastness of space. And yet, for all the distance and all the difficulty and all the engineering challenges and all the radiation damage and all the years of patient waiting, we have learned things about Jupiter that no previous generation of humans ever knew. We have peered beneath the clouds and found structure and motion, reaching down thousands of kilometers into the dark. We have mapped a magnetic field more complex and more powerful than anything else in the planetary realm. We have discovered that the core of Jupiter is not what we expected, that the planet's formation may have been more violent and more interesting than our simple model suggested. We have seen cyclones arranged in geometry, storms layered like the rings of a tree, aurora blazing with energy enough to power civilizations. The storms are not hiding anything, not in the sense that a secret implies something deliberately concealed, but they are covering something, obscuring the deeper reality beneath the beautiful weather that has captivated observers for 4 centuries. Juno has lifted the veil just enough to show us that the true nature of Jupiter is far more complex and far more interesting than the clouds alone could ever reveal. And that is perhaps the most important discovery of all, not any single finding about wind depths or core structure or magnetic geometry, but the recognition that this world we thought we knew is still capable of surprising us, still full of mysteries waiting to be uncovered. Consider, for a moment, what the next decade might bring. Juno's mission will eventually end, but the questions it has raised will inspire new missions, new instruments, new ways of probing the giant planets. The Europa Clipper, already on its way as these words are spoken or will be soon, will study the icy moon in detail, investigating its potential for harbouring life. The JUICE mission, launched by the European Space Agency, will explore Ganymede and the Jovian system more broadly, and perhaps someday a mission will return to Jupiter itself with instruments even more capable than Juno's, penetrating deeper into the mysteries that remain, answering questions we have not yet thought to ask. The story of Jupiter is not finished. It is barely begun, despite 4 centuries of telescopic observation and nearly a decade of close orbital study. Each discovery raises new questions, each answer reveals new depths of complexity. This is the nature of scientific exploration, that the horizon always recedes before us, that the more we learn, the more we realize how much remains to be learned. Jupiter will keep its deeper secrets for a while longer, hidden beneath the endless storms, waiting for the next generation of spacecraft and the next generation of scientists to come seeking them. It is worth trying just once to feel the weight of time that Jupiter represents. The planet formed in the solar nebula more than 4.5 billion years ago, and it has been orbiting the Sun ever since, accumulating its vast atmosphere, generating its magnetic field, spinning out its radiation belts, hosting its storms. Entire geological eras have come and gone on Earth, while Jupiter circled patiently in the outer darkness. The dinosaurs rose and fell while Jupiter spun. Human civilization flickered into existence, a brief candle flame in the cosmic night, and Jupiter continued its ancient circuit, unchanged by our presence, unaware of our gaze. Whatever future awaits our species, whether we spread to the stars or perish in some calamity, Jupiter will likely continue, the storms churning, the cyclones spinning, the great planet pursuing its slow orbit around a slowly aging sun. There is something almost comforting in that indifference, in the knowledge that Jupiter does not need us to witness its majesty in order to be majestic. The storms will churn whether or not anyone is watching. The magnetic field will sweep its invisible currents through space whether or not any instrument is there to measure them. The cyclones at the poles will hold their strange formations whether or not any eye, human or mechanical, ever looks upon them again. Jupiter exists for itself, by itself, in a way that most things we care about do not. Our cities need us, our gardens need us, our stories need us to tell them. But Jupiter simply is, and will continue to be, long after the last transmission from the last spacecraft has faded into the background hum of the cosmos. And yet we keep reaching toward it, keep sending our small machines on their long journeys, keep pointing our telescopes at that distant point of light. We do this not because Jupiter needs our attention, but because we need to give it, because something in the human spirit refuses to leave the distant and the vast unexplored. The storms of Jupiter are beautiful, yes, but they are also a question, and questions call to us across any distance. What lies beneath? What forces drive the endless motion? What secrets does the deep hold that the surface does not reveal? These are the questions that sent Juno on its journey, and these are the questions that will send whatever comes after. Let us sit for a long moment with the idea of what it means to explore a world you can never land on. Every other target of human curiosity, from the moon to Mars to the asteroids, offers at least the theoretical possibility of boots on the ground, of human hands touching alien rock. Jupiter denies us this completely. There is no surface to stand on, no solid place where a future explorer might plant a flag or collect a sample. The planet is all depth, all atmosphere, all gradual transition from gas to liquid to something stranger still. To explore Jupiter is to explore from a distance, always to peer into its depths with instruments that can never quite reach the bottom, to circle above its storms knowing that descent would mean dissolution. The slow, crushing embrace of pressure beyond anything material can withstand. This limitation shapes everything about how we study the giant planet. Our spacecraft cannot land, cannot sample, cannot touch. They can only observe, measure, infer. Juno carries no landing legs, no sample containers, no drills or scoops. It carries eyes and ears of a very different kind, instruments designed to sense what cannot be grasped. The microwave radiometer peers through the clouds by catching the faint thermal glow rising from below. The gravity science experiment detects the shape of the interior by measuring how the spacecraft's path bends as it falls past hidden masses. The magnetometer traces the field lines that thread through space, painting an invisible portrait of the churning metallic hydrogen deep within. Every discovery Juno has made has been an act of interpretation, a translation from raw data into understanding, a reconstruction of the hidden world from the signals it sends outward. There is something profound in this method of exploration, something that connects to how we understand anything distant or difficult, or closed to direct inspection. We cannot see the past directly, but we can read its traces in rocks and fossils in the light of ancient galaxies. We cannot touch the interior of an atom, but we can infer its structure from how particles scatter and energies shift. We cannot enter the minds of others, but we can listen to their words and watch their actions and build a picture of what lies within. Juno does for Jupiter what all inquiry does for the unreachable. It finds the signals that leak outward from hidden depths and learns to read them, patiently, carefully, building understanding from inference rather than direct contact. Return with me, one more time, to the question that began this journey. What has Juno found hiding beneath Jupiter's endless storms? The answer, we now know, is not a single thing, but a cascade of revelations, each one opening onto the next. Beneath the clouds lies wind that reaches down thousands of kilometers into the dark, wind that represents a significant fraction of the planet's mass, wind that defies the simple expectation that weather should be shallow and decoration should be separate from structure. Beneath the wind lies the gradual transition to liquid, hydrogen compressed beyond any gas we know, flowing in currents that generate the mightiest magnetic field of any planet. Beneath the liquid lies the metallic sea, hydrogen squeezed so tight that its electrons wander free, conducting electricity, amplifying the dynamo that powers the magnetic field and the radiation belts that guard the planet. And at the very centre, where we expected a distinct core of rock and ice, lies instead a blurred and diluted heart, fuzzy with dissolved material, testament to an ancient impact, or perhaps simply to the strange physics of matter, under pressures we can barely imagine. These are the findings, but they are not the true discovery. The true discovery is that Jupiter remains full of questions, that every answer Juno has provided has revealed new mysteries, that the planet we thought we knew from 4 centuries of telescopic observation is stranger and more complex than we ever supposed. The storms are not a mask hiding a simple interior. They are the surface expression of processes that reach all the way to the core, structure and weather intertwined in ways that blur the boundaries we thought we understood. Spare a thought too for the storms themselves, those beautiful swirling patterns that first drew human eyes to Jupiter and held our gaze for generations. They are not mere decoration. They are not cosmetic features painted on the surface of a solid globe. They are deep expressions of the planet's nature, roots reaching down into the dark, structure extending through a significant fraction of the planet's radius. The Great Red Spot is not a blemish on the skin of Jupiter, but a window into its soul, a vortex that touches depths no human eye will ever see directly. The bands that stripe the planet are not painted lanes, but the visible edges of vast atmospheric rivers, flows that extend far below the clouds and shape the world in ways we're only beginning to understand. It is worth pausing on the question of beauty itself, on why we find Jupiter's storms so captivating. There is colour there, yes, reds and oranges and subtle shades of brown that warm artists have tried to capture for centuries. There is pattern, the regular alternation of zones and belts, the geometric perfection of the polar cyclones, the smooth oval of the Great Red Spot. There is motion, the slow drift of features visible from Earth through small telescopes, the confirmation that what we see is alive in some sense, changing, evolving, never quite the same from one observation to the next. But there is something more than these elements, something harder to name. Perhaps it is the combination of familiarity and strangeness, the recognition of patterns that seem almost like weather we know stretched to scales that dwarf anything in human experience. Perhaps it is the suggestion of depth, the intuition that what we see on the surface is only the beginning of something vast. Perhaps it's simply the power of the distant and the large to move us, the same impulse that draws our eyes to mountains and oceans and the night sky itself. Whatever the source of that beauty, Juno has deepened it rather than dispelled it. We might have feared that close inspection would reduce Jupiter to mere data, strip away the mystery and leave only facts. Instead, the opposite has happened. Each discovery has revealed new layers of complexity, new reasons for wonder, new questions to pursue. The Great Red Spot is more astonishing now that we know it reaches hundreds of kilometers deep than it was when we imagined it as a shallow surface feature. The banded winds are more impressive now that we understand they extend thousands of kilometers into the interior than they were when we thought them confined to a thin atmospheric shell. The polar cyclones are more mysterious now that we have seen them holding their geometric formations for years, stable in ways we cannot yet fully explain. Consider for a moment the experience of a single orbit, a single pass of Juno over the cloud tops of Jupiter. The spacecraft approaches from the distant reaches of its ellipse, falling inward for days as the planet grows from a point of light to a visible disk to a world filling the sky. It crosses the boundary of the magnetosphere, the bow shock where the solar wind meets Jupiter's magnetic influence, and enters a realm of charged particles and invisible forces. It falls faster and faster, accelerating under the pull of the planet's immense gravity, until it is sweeping over the cloud tops at speeds that would carry it from New York to Los Angeles in less than a minute. For 2 hours, perhaps a little more, it is close enough to make its measurements, close enough for the microwave radiometer to peer through the clouds and the magnetometer to map the field and the camera to capture images of unprecedented detail. Then it swings away, climbing back toward the apex of its orbit, the data stored in its memory waiting to be transmitted home at the slow pace the distance allows. Each of these passes is an event, a brief window of opportunity that the mission team has planned for years. The geometry must be right, the spacecraft must be healthy, the instruments must be functioning, the data must be captured and stored and eventually transmitted. There is no second chance. If something fails during the close approach, the opportunity is lost forever. And yet the team has executed dozens of these passes successfully, each one adding to the portrait of Jupiter's hidden nature, each one bringing home data that will be analysed for years to come. Picture, if you can, the control room during one of these close approaches. Not the dramatic countdown of a launch, not the nail-biting tension of a landing attempt, but something quieter and more sustained. The spacecraft is far beyond real-time control, its signals taking minutes to cross the void between Jupiter and Earth. The team watches the telemetry, the health indicators, the confirmation that data is being recorded, knowing that by the time they see any sign of trouble, the moment of trouble will be long past. They wait, they hope, they trust in the engineering and the planning, and the thousands of decisions made over years of preparation. And when the close approach is complete, when the data begins to trickle home, there is a particular kind of satisfaction, the reward of patience and precision applied over distances that dwarf human imagination. There is one more thing worth understanding about Juno's journey, something that connects it to the deeper story of human exploration. Every spacecraft we send to the outer solar system is, in a sense, a message to ourselves. It is a statement of what we value, of what we think is worth knowing, of how we choose to spend our resources and our attention. Juno was built and launched because enough people believed that understanding Jupiter was important, that the questions it might answer were worth the cost and the effort and the years of waiting. The spacecraft itself is a physical embodiment of curiosity, of the human refusal to leave the distant and the unknown unexplored. And there is something gentle about this, something that has nothing to do with competition or conquest, or any of the motivations that sometimes drive human endeavour. Juno was not sent to claim Jupiter, or to exploit its resources, or to establish any kind of dominion. It was sent to look and to listen, to observe and to understand. Its instruments do not change the planet they study. Its presence makes no difference to the storms or the magnetic field or the deep interior. Jupiter continues exactly as it would have continued if Juno had never existed, spinning and churning and hosting its ancient weather in perfect indifference. The only thing that changes is us, our understanding, our picture of what lies out there in the dark. This is perhaps the purest form of exploration, the kind that seeks knowledge for its own sake, that reaches toward the distant not to take but to learn. There are practical reasons to study Jupiter, of course, things we might discover that inform our understanding of planetary formation, or our ability to detect planets around other stars, or our comprehension of magnetic fields and their effects. But these practical considerations feel almost like afterthoughts, justifications offered to satisfy those who need reasons beyond wonder itself. The real motivation, the thing that has drawn human eyes to Jupiter for centuries and human spacecraft for decades, is simpler and more profound. We want to know. We want to understand. We want to see what lies beneath the beautiful storms. Let us return, one final time in this movement, to the image of Jupiter as it appears in the night sky. A bright point of light, steadier than the stars around it, moving slowly against the background of fixed constellations. This is what Galileo saw when he turned his primitive telescope toward it and discovered the 4 large moons that now bear his name as a group. This is what generations of astronomers saw as they traced the Great Red Spot and measured the rotation period and catalogued the changing patterns of the bands. This is what any of us can see on a clear night if we know where to look, a world visible to the naked eye, familiar and yet impossibly distant. Everything Juno has discovered lies hidden in that point of light. The deep winds, the fuzzy core, the lopsided magnetic field, the geometric cyclones at the poles, the auroral ovals blazing with energy, the ammonia storms bubbling up from below. All of it is there, compressed into a single bright dot in the evening or morning sky, waiting for anyone patient and curious enough to wonder what secrets it might hold. The distance between that point of light and the detailed portrait Juno has assembled is the distance travelled by 4 centuries of technology and dedication, by telescopes growing larger and spacecraft growing more capable, and questions growing deeper as each answer reveals new mysteries. And that distance will continue to grow. Future generations will see Jupiter with eyes we cannot imagine, instruments we cannot conceive, from perspectives we cannot predict. They may answer questions that Juno's data raised but could not resolve. They may discover things that would astonish us as much as Juno's findings would have astonished Galileo. The story of Jupiter's exploration is not a story with an ending, but a story that stretches forward into a future we cannot see, carried by the same curiosity that first turned telescopes toward the wandering light and found it to be a world. It is worth trying just once to feel the full weight of what Juno has accomplished. A spacecraft the size of a basketball court, powered by the faint sunlight of the outer solar system, orbiting a world more massive than all the other planets combined, dropping close to cloud tops swirling with storms that could swallow Earth, peering through atmospheres with microwaves and tracing fields with magnetometers, and capturing images of alien beauty no human eye will ever witness directly. All of this unfolding over years, in patient accumulation, discovery by discovery, orbit by orbit, data point by data point. The sum of it is a portrait of Jupiter more detailed and more surprising than any that came before, a gift from human ingenuity to human understanding, a small light cast into the darkness that illuminates something vast and wonderful. The storms are not hiding anything, not in the sense that implies deception or concealment. They are simply being what they are, atmosphere in motion, weather on a scale that dwarfs our categories and confounds our expectations. But beneath them lies depth, structure, complexity, mystery, all the things that Juno has begun to reveal, and that future missions will continue to explore. The endless storms are the beginning of the story, not the end. They are the door through which we have learned to peer, and what lies beyond that door is more strange and more beautiful than we ever imagined, when we first looked up at that bright wandering light and wondered what it might be. And perhaps that is the truest thing we can say about Jupiter, after all these years of watching and wondering, and finally, with Juno beginning to understand. It is not a world that yields its secrets easily. It does not present itself the way the rocky planets do, with surfaces you can map and craters you can count, and geology you can reconstruct from visible evidence. Jupiter asks something different of us. It asks that we learn to see depth where we once saw only surface, to find structure where we once saw only chaos, to recognize that beauty and mystery are not opposites, but companions, each deepening the other in ways we're only beginning to appreciate. Consider, for a moment, the generations of human beings who have looked up at that bright point of light without knowing what Juno has now revealed. They saw the same wandering star that we see, the same steady glow that outshines everything in the night sky except Venus and the moon. They gave it names, Jupiter and Zeus and Marduk and Brihaspati, names that carried weight and meaning, names that placed it among the gods because something about its brightness and its slow majesty seemed to deserve reverence. They watched it move against the background of fixed stars and tried to understand what that motion meant, building models of the cosmos that put Earth at the centre, or the sun at the centre, or the divine at the centre, always trying to make sense of that wandering light and its place in the grand order of things. None of them knew about the great red spot sinking hundreds of kilometres into the atmosphere. None of them knew about the jets of wind reaching thousands of kilometres down into the dark. None of them knew about the fuzzy core or the metallic hydrogen ocean, or the geometric cyclones spinning at the poles in patterns that seem almost too regular to be natural. They looked at the same light we look at, but they saw a different world, a simpler world, a world that fit more comfortably into their understanding of what planets could be. What Juno has given us is not just data or images or discoveries, though it has given us all of those things in abundance. What it has given us is a Jupiter that is stranger and more complex and more wonderful than the Jupiter our ancestors imagined, a world that exceeds our expectations in every direction, that surprises us with its depth and its structure, and its capacity to hold mysteries we had not even thought to ask about. The distance between the Jupiter of ancient skywatchers and the Jupiter of Juno's instruments is a measure of how far human understanding can travel when it is carried by curiosity and ingenuity and patience. It is the distance between a point of light and a world, between a name and a place, between reverence based on mystery and wonder based on knowledge. Spare a thought too for the spacecraft itself, still circling that enormous world as we speak, still gathering data, still sending its findings home across the vast emptiness that separates Jupiter from Earth. Juno has been in orbit for years now, and it has endured conditions that would destroy most machines built by human hands. The radiation environment around Jupiter is among the most intense in the solar system, a consequence of that powerful and lopsided magnetic field trapping charged particles and accelerating them to tremendous energies. Juno carries its most sensitive instruments inside a titanium vault designed to shield them from this bombardment, a kind of armoured heart protecting the electronics that make its mission possible. But even with this protection, the radiation takes its toll. Every orbit, every close approach, every pass through the most intense regions of the radiation belts degrades the spacecraft a little more. Its systems grow slightly less reliable, its components slightly more vulnerable, its remaining lifetime slightly shorter. And yet it continues. Orbit after orbit, periove after periove, Juno swings close to the cloud tops and peers downward with its instruments and sends back what it finds. The patience of the spacecraft mirrors the patience of the scientists who interpret its data, and the engineers who designed and built it, and the generations of researchers whose work made the mission possible in the first place. This is what exploration looks like when the destinations are measured in hundreds of millions of miles, and the journeys are measured in years and decades. It is not the dramatic exploration of flags planted and footprints left behind, though perhaps someday that kind of exploration will reach Jupiter's moons, if not Jupiter itself. It is the quiet exploration of instruments and signals, of data transmitted across unimaginable distances, of discoveries made not in a single thrilling moment, but in the slow accumulation of evidence over time. Return with me, one more time, to the Great Red Spot, that ancient storm that has become the symbol of Jupiter in the popular imagination. When Juno arrived and turned its microwave radiometer toward this famous feature, it found something that reshaped our understanding of what we were looking at. The spot is not a shallow disturbance floating on top of the atmosphere, like foam on the surface of water. It extends downward, far downward, reaching depths of perhaps 200 kilometers or more below the visible cloud tops. Its roots sink into regions where the pressure and temperature are nothing like the conditions at the surface, where the atmosphere transitions into something denser and stranger, where the physics of weather as we understand it begins to give way to the physics of planetary interiors. The Great Red Spot is not just a storm, it is a structure, a persistent feature of Jupiter's atmosphere that has maintained its identity and its approximate position for centuries despite the chaotic swirl of weather around it. Juno has shown us that this persistence is not a surface phenomenon but a deep one, that the spot is anchored somehow in the layers below, held in place by forces and flows that we are only beginning to map. And yet, for all its depth, the Great Red Spot is changing. Observations over the past century have shown it shrinking, its long axis growing shorter, its shape becoming more circular. The spot that 19th century astronomers sketched was larger than the spot that 20th century astronomers photographed, and the spot that Juno orbits today is smaller still. No one knows exactly why this is happening or what it means for the storm's future. Perhaps it will stabilize at some smaller size and persist for centuries more. Perhaps it will continue to shrink until it dissipates entirely, leaving Jupiter without its most famous feature for the first time since human beings have been watching. Perhaps something else will happen, something we cannot predict because we do not yet understand the deep dynamics that govern these giant atmospheric structures. But silence is not the same as gone. Even if the Great Red Spot were to vanish tomorrow, Jupiter would remain what it has always been, a world of storms beyond counting, a world where weather operates on scales that dwarf anything in human experience, a world whose atmosphere extends down and down into depths we have only begun to explore. The spot is one feature among many, one mystery among thousands, one small part of a planet that defies easy summary or simple understanding. Its possible disappearance would be a loss, certainly, a break in the continuity of observation that stretches back to the 17th century. But it would not be an ending. The storms would continue, the bands would flow, the cyclones would spin at the poles, and the vast processes that make Jupiter what it is would carry on, as they have carried on for billions of years before any human eye ever looked upward and noticed that wandering light. There is one more thing worth understanding about what Juno has found, something that touches on the deepest questions we can ask about this enormous world. It concerns the core, that mysterious central region where the planet's origin story is written in the arrangement of heavy elements. Before Juno, the standard picture was reasonably clear. Jupiter formed from a core of rock and ice, perhaps 10 to 20 times the mass of Earth, that grew large enough to begin capturing the hydrogen and helium that make up the bulk of the planet's mass today. The heavy elements that seeded this process should have remained concentrated at the centre, a dense nucleus around which the rest of the planet accumulated. It was a tidy picture, a satisfying picture, a picture that made intuitive sense. Juno found something different. The gravity measurements, exquisitely precise, revealed that the heavy elements are not concentrated at the centre in a sharp, well-defined core. Instead, they are spread outward, diffused through a large volume, blurred in ways that the simple formation picture did not predict. The core is fuzzy, diluted, as though something stirred it after formation, or the formation process itself was more complex and violent than we had assumed. One possibility is that early in Jupiter's history, while it was still gathering mass and still hot from its formation, a massive object collided with it and mixed the core material outward, disrupting the neat layering that we expected to find. Another possibility is that convection currents in the deep interior have gradually eroded the boundary between the core and the envelope above it, blending heavy elements upward over billions of years. The data do not yet tell us which scenario is correct, or whether the truth involves some combination of these processes or something else entirely. What the fuzzy core tells us, whatever its origin, is that Jupiter's interior is not the simple onion-like structure that textbook diagrams once suggested. It is more complicated, more dynamic, more shaped by history and process than we imagined. The planet remembers its formation in the distribution of its elements, but that memory is not a clear record. It is smudged and altered by billions of years of internal dynamics, by impacts and convection, and the slow rearrangement of matter under pressures that no laboratory on Earth can replicate. Juno has given us a glimpse of this history, a partial reconstruction of events that happened when the solar system was young and Jupiter was still becoming what it would be. But the glimpse is just that, a beginning, an invitation to look deeper and learn more. Picture, if you can, what it would be like to descend through Jupiter's atmosphere, to pass through the cloud layers that Juno photographs and into the darkness below. The pressure would build steadily, the temperature would rise, the composition of the atmosphere would shift as you move through different chemical regimes. Eventually you would reach depths where the hydrogen around you would no longer behave like a gas at all, where it would become so compressed that its electrons would flow freely like the electrons in a metal, where the substance surrounding you would be neither gas nor liquid nor solid in any familiar sense, but something genuinely alien, a form of matter that exists nowhere on Earth and perhaps nowhere else in the solar system except deep inside the other giant planets. Somewhere in this metallic hydrogen ocean, currents would be flowing, driven by the planet's rotation and by heat rising from below, and these currents would be generating the magnetic field that Juno has mapped, the lopsided asymmetric field that hints at the complexity of the processes occurring in regions no instrument has ever seen directly. You would never reach a surface, because there is no surface to reach. The transition from atmosphere to interior is gradual, a continuous increase in density and pressure and strangeness, with no sharp boundary where you could say that one region ends and another begins. This is what it means for Jupiter to be a gas giant, a world without the solid ground that we instinctively expect when we think of planets. The storms we see from outside are the outermost layer of something that extends all the way down to the centre, a continuous fluid envelope surrounding a diluted core, everything connected, everything in motion, everything shaped by forces operating on scales we struggle to comprehend. And we cannot leave this story without acknowledging what comes next, what the future holds for our understanding of this extraordinary world. Juno's mission was extended beyond its original timeline, allowing it to make additional discoveries and fill in gaps in its coverage. But eventually, like all spacecraft, it will reach the end of its operational life. The plan has always been to dispose of Juno safely, to send it diving into Jupiter's atmosphere so that it cannot contaminate the moons that might harbour conditions suitable for life. When that day comes, the spacecraft will make one final plunge, transmitting data for as long as it can before the increasing pressure and temperature destroy its systems. It will become part of Jupiter, its atoms mingling with the vast atmosphere it spent years studying, its mission complete. But the knowledge it gathered will remain. The papers will be written, the data will be archived, the discoveries will be incorporated into textbooks and lectures, and the quiet understanding that accumulates whenever human beings learn something new about their universe. Future spacecraft will build on what Juno found, asking questions that Juno's data made possible, reaching for depths and details that Juno could not access. The Europa Clipper, already on its way as of this telling, will examine one of Jupiter's moons with instruments designed to search for signs of habitability beneath its icy crust. Other missions are proposed, debated, designed, some of them focused on Ganymede or Callisto, some of them carrying instruments that could probe the atmosphere or the magnetic field in new ways. The exploration of the Jupiter system is not ending, it is continuing, building on what Juno learned, reaching for answers to questions that Juno's discoveries have made more pressing and more profound. So let us ask it one more time, the question we began with, the question that has carried us through this long exploration. What has Juno found hiding beneath Jupiter's endless storms? The honest answer, the complete answer, is that it has found depth. Not just physical depth, though there is plenty of that, thousands of kilometers of atmosphere descending into darkness before giving way to hydrogen made metallic by pressure, and then eventually to a diluted core whose boundaries are blurred beyond easy definition, but also depth of complexity, depth of process, depth of history. Jupiter is not the simple giant that older generations imagined. It is a world where storms sink their roots deep into the dark, where winds blow at depths no sunlight reaches, where the magnetic field is shaped by currents in an ocean of metallic hydrogen, where the core carries the smudged memory of a violent formation. It is a world that rewards patience and precision, that reveals its secrets only to instruments capable of peering through its clouds and measuring its gravity and tracing its fields with exquisite accuracy. And beneath all of this complexity, beneath the storms and the winds and the core and the magnetic field, there is something simpler. There is a planet, the largest in our solar system, doing what planets do, holding itself together with gravity, radiating away the heat of its formation, spinning once every 10 hours and driving the weather patterns that flow around its middle latitudes. Being what it has been for 4.5 billion years, long before any eye looked up from Earth and noticed its steady light, and what it will continue to be for billions of years more, long after Juno's atoms have dispersed into its clouds and the spacecraft's mission has become a chapter in the history of exploration. Tonight, if the sky is clear and you know where to look, you can see Jupiter for yourself. It will appear as a point of light, bright and steady, moving slowly against the background of stars over the course of weeks and months. Everything we have discussed is there, compressed into that single dot, waiting. The great red spot is there, and the polar cyclones and the deep winds and the metallic hydrogen ocean and the fuzzy core. The magnetic field is there, crackling with radiation and shaping the space around the planet into an invisible architecture of force. The history is there, 4.5 billion years of it, written in the distribution of elements and the dynamics of the interior and the slow changes that have shaped the atmosphere over timescales we can barely imagine. Juno found all of this hiding beneath the beautiful storms. It found that the surface we thought we were seeing was not a surface at all, but a beginning. The outermost layer of something that extends down and down into regions stranger than we imagined. It found that Jupiter rewards those who look past the obvious and ask what lies beneath. It found that even a world we have watched for 4 centuries can still surprise us, can still reshape our understanding, can still remind us how much we have yet to learn. The spacecraft is still out there tonight, circling that enormous world, gathering data, sending it home. The people who built it and launched it and operate it are still at work, planning the remaining orbits, analysing the incoming information, writing papers and giving talks and teaching students who will carry the work forward. The curiosity that sent Juno to Jupiter is the same curiosity that turned Galileo's telescope toward that wandering light 400 years ago. The same curiosity that will send future missions to places we cannot yet name. It is the thread that connects all of this, the human impulse to look up at something beautiful and strange and ask what secrets it might hold. Jupiter is still out there tonight, holding its secrets and slowly giving them up to anyone patient and ingenious enough to seek them. It will be there tomorrow night and the night after, and for longer than human civilization has existed. The storms will continue their endless motion, the bands will flow, the great red spot will shrink or grow or vanish or persist. And somewhere, someone will look up at that bright, steady light and feel the pull of curiosity that has carried us this far, the desire to know what lies beneath the beautiful surface, the willingness to build machines and send them across hundreds of millions of miles to find out. Thank you for making this journey with me tonight, down through the clouds of Jupiter and into the depth that Juno has revealed. Keep looking up, take good care of one another, and good night.